Section 1. Introduction to Quantum Tunneling. Quantum tunneling sounds like a concept from a sci-fi movie, yet it's a real phenomenon that defies the classical laws of physics. Imagine throwing a ball at a wall expecting a collision, but instead, the ball goes through the wall without destroying it. That's the kind of surprising behavior quantum particles can exhibit due to quantum tunneling. This concept is not just a curious detail, but a fundamental aspect of quantum mechanics, offering deep insights into the behavior of particles at microscopic levels. In classical physics, particles like electrons are depicted distinctly as particles. However, in the quantum world, these particles can sometimes act like waves, capable of doing things that seem impossible by classical standards. Understanding quantum tunneling requires us to step into a world where particles can penetrate barriers that, according to classic physics, should be impenetrable. Quantum tunneling challenges our everyday experiences and expectations about how the physical world operates. It is a perfect example of quantum weirdness and is integral to many technologies that shape our modern world. Section 2. Wave-particle duality, the dual nature of matter. Wave-particle duality is a fundamental concept in quantum mechanics, proposing that every particle or quantum entity can exhibit both particle-like and wave-like behavior. It's like if you could be both a person and a wave of light, depending on the situation. This concept was first brought to light by the famous double-slit experiment, which showed that electrons can exhibit wave-like properties, creating interference patterns that are typical of waves. Understanding this duality is crucial for grasping how quantum tunneling works. If particles were strictly particles, they couldn't just pass through barriers. However, their wave-like nature allows them to spread out and sometimes move through physical barriers, much like a sound wave spreads through the air. This is where the classical intuition about the world begins to falter, making room for quantum insights. The implications of wave-particle duality are profound. It suggests that the very nature of reality at the smallest scales is far different from our everyday experiences. In the quantum world, things don't just exist in simple, predictable states. Instead, they show probabilities and possibilities, challenging our traditional views of how the universe works. Section 3. Barrier potential, understanding quantum barriers. In quantum mechanics, a barrier potential is essentially a hill or wall that a particle encounters. In the classical world, if a particle doesn't have enough energy to climb over a barrier, it simply won't. It's like not having enough gas in your car to get over a hill. However, in the quantum realm, particles can sometimes behave differently and pass through these barriers, even without sufficient energy. This phenomenon is known as tunneling. Consider the barrier as a test of possibility. From a quantum perspective, even though a particle, like an electron, might not have enough energy to traditionally overcome a barrier, its wave nature allows it to leak through this barrier. It's a bit like a ghost walking through walls. A concept that our everyday logic struggles to accept, but is nonetheless true in the quantum realm. This ability to tunnel through barriers leads to some of the most intriguing and perplexing phenomena in physics. It defies classical logic and introduces a level of unpredictability that is central to quantum mechanics. Understanding how particles interact with potential barriers is key to mastering the concept of quantum tunneling and its myriad implications in the real world. Section 4. The role of wave functions in quantum mechanics. Wave functions are at the heart of quantum mechanics. They provide a mathematical description of the quantum state of a particle. In simpler terms, a wave function is a formula that helps predict where a particle like an electron might be found and what it might be doing. It's not just about location, but also about the probability of finding the particle in various states. In the context of quantum tunneling, the wave function describes how the particle's wave-like nature is distributed in space and time. When a particle encounters a barrier, its wave function doesn't just stop at the barrier. Parts of it can extend to the other side. This extension represents the probability of the particle appearing on the other side of the barrier, effectively tunneling through it. This concept can be quite challenging to visualize because it doesn't align with anything we experience in the macroscopic world. However, It's a fundamental aspect of how particles behave at microscopic scales. The wave function is crucial for understanding not just where a particle is, but also its potential to appear in seemingly forbidden regions, like on the other side of a barrier.